So good morning to all. This is Anvesh from Triple Branch. So today my topic is about the thermal power system of subject of power system operation and controls. So basically the power system, the thermal power system generation or the thermal power system. So we can call it as the thermal system, the thermal power generation or else thermal power station. So let's begin with the key learnings. So basically, what is meant by a what is the definition of the thermal power plant? So a thermal power plant is defined as facility that generates electricity by using heat energy, primarily from burning coal to produce steam that drives turbine. Working principle of the thermal power plant. The working principle involves burning coal to produce steam, which spins a turbine connected to a generator, converting the thermal energy into electrical energy. Steam cycle. In steam cycle, water is heated into steam, which expands and spins the turbine, then is cooled and condensed back into water to be reduced. Efficiency of thermal power plants. The efficiency of thermal power plants as the ratio of electrical output to heat energy input with a value typical from 20 to 26 percentage. So basically what is a thermal plant? So a thermal plant generation or thermal power station is the most conventional source of electric power. The thermal power station or the power plant is also referred as a coal thermal power plant and steam turbine power plant. So So basically the theory of the thermal power station. So the theory of the thermal power station is simple. These plants use steam turbines connected to the alternators to generate electricity. The steam is produced in high pressure boilers. So generally in India, bitumen coal, brown coal and peat are used as fuel for the boilers. The bituminous coal is used as boiler fuel, has volatile matter from 8 to 33% and ash content 5 to 16%. To increase thermal efficiency, coal is used to boil in powder form. In the coal thermal power plant, the steam is produced at high pressure in the boiler due to the burning of fuel in boiler furnace. This is the further superheated in superheater. So, this superheated steam then entered into the turbine and rotates the turbine blades. The turbine is mechanically so coupled with an alternator that will rotate with the rotation of turbine blades. So when steam enters the turbine, its pressures drop rapidly, causing the steam volume to the increase. After imparting energy to the turbine rotor, the steam passes out of the turbine blades into the condenser. So in the condenser, the cold water is circulated with the help of pump which condense the low pressure wet steam. So this condensed water is further supplied to a low pressure water heater where the low pressure steam increases the temperature of this feed water. It again regains the pressure. So to understand better, let's break down the steps how thermal power system operates. So let's begin the step one. So first, uh, the pulverized coal is burned into the furnace of steam boiler. So next step two, the high pressure steam is produced in the boiler. So next step three, the steam is then passed through the superheater where it is further heated up. So next step four, the superheated steam is then entered into a turbine at high speed. So next, the last step, the turbine is steamed forced, rotates the turbine blades. That means here in the turbine, the stored potential energy of high pressurized steam is converted into the mechanical energy. So this is the schematic diagram of the thermal plant. So when if you see here from the left side of my from the left side of the screen, there is a chimney, and there is a dust collector of a precipitator, and there is a coal hopper, and there is a pulverizer. There is a preheat air, a furnace, a boiler, a steam, a feed water, a condenser, a feed water pump, and a turbine and a alternator. So this is a schematic diagram of the thermal power plant. So after rotating the turbine blade, the steam has lost its pressure and pass out of the turbine blades and enters into a condenser. So in the condenser, the cold water is circulated with the help of a pump, which condenses the low pressure wet steam. So this condensed water is then further supplied to a low pressure water heater, where the low pressure steam increases the temperature of this feed water. So it is then again heated in a high pressure heater, where the high pressure of steam is used for heating. So the turbine in the thermal power system, in the thermal power station, acts as a prime mover of the alternator. So the optimal operation of generators in the thermal power station. So the optimal operation of generators in thermal power system power stations are also known as the economic dispatch. Involves determining the most cost efficient way to distribute the demand across multiple generators while satisfying system constraints. The goal is to minimize the operational cost of power generation, typically fuel's cost, while ensuring the system safety, reliability, and environmental regulations. So next, some key factors and methods involved in the optimizing the operation of generation in a thermal power station include. So this is economic dispatch, so we can call it is EED. So the main objective of this economic dispatch is to minimize the total fuel cost while satisfying power demand. So next, the cost function. So the fuel cost for the generator is typically represented as the quadratic cost function of the power output. So the power balance constraint, so the sum of the power outputs of all generators must meet the total load. So the PI load equal to sum of the PI. So the generator limit, each generator has a lower and upper limit. So P minimum is greater than or equal to Pi and greater than or equal to P max. So this is a power generation limit. So next, the unit commitment. So you see the objective, the schedule that on or off status of a generator over a time horizon while minimizing cost. So the minimum up down time. So each generator must remain on for a minimum period of once started and off for the minimum period once shut down. So startup and shutdown costs. So these costs must be considered when turning generators on or off. So low demand and spinning reverse. So the system must meet low demand in enough reverse capacity to handle sudden changes in a load or a generator factors. So that a penalty for environmental emissions. Some optimization models are inappropriate penalties for environmental emissions such as CO2 and or NOx emissions into the objective function. This encourages the operation of generators in a more environmental friendly manner. So the method for the optimization. So lambda iteration method, a classical method used for solving the economic dispatch problems. It iteratively adjusts the marginal cost lambda to the balance power among generators. Large range multipliers used to solve the constraint optimization problems by introducing a large range multiplier for the power balanced constraints. So dynamically programming, often used for unit commitment problems, where it evaluates the cost of different generator on off combination over time. So linear programming on and quadratic programming. So these are the mathematical optimization methods used for complex models. Multiplier constraints and are involved. So heuristics and meta heuristics methods. So techniques such as a genetic algorithm, GA, particle swarm optimization PSO, and simulated analyzing assay are used for solving highly nonlinear complex optimization problems where classical methods struggles. So heat rate of fuel efficiency, the heat rate of each generator, which is amount of fuel energy required to produce 1 unit of electricity, is crucial in determining its operational efficiency. The goal is to operate generators at points of optimal fuel efficiency used to mine high load level where there is a heat rate is lower. So this is a thermal power station diagram. So whatever the schematic diagram I have said in the previous slide, so this is the actual diagram. So thank you.